Okay. Right, the reason being is that my colleague was recording it for me. So let's continue. Right, okay, so thank you all very much for coming. Welcome. This is a web seminar that's been brought to you by Kuraray and underlines their commitment towards serving the ever-changing demands of the global glass industry through innovation and leadership. Thank you for joining us for this fantastic webinar on laminated glass with structural interlayers, which played a key part in the new Musée Atelier, which the English translation is Museum Workshop, for the Audemars Piguet, who have devised endlessly inventive horological masterpieces, and this building design is perfectly reflective of that. We are honoured and privileged to introduce our guest speaker today, Mr. Philippe Villerat, who is the partner at Lushinger Meyer, where Philip leads the facade and engineering team. He graduated as a facade engineer at the Lausanne University in 2004. He is in charge of various key projects and is on the board of the Swiss Facade Association, and this links the consultancy perfectly to the facade industry. This seminar will be added to our collection of training sessions designed to help with the specification and the choice of products to use for certain laminated glass applications, and you will find these all on our website. Before I hand over to Philip, I wanted to run through some quick housekeeping. Your audio and visual has been turned off to aid the quality of this presentation. There is a facility for you to raise questions at the bottom right of the screen, and you'll see there are a variety of icons. The one shaped like a speech bubble enables you to post questions. If, and I'm sure we will have time, we'll go through these at the end, or we can reply to them individually afterwards. We are also recording this presentation for those that are unable to attend, or for those that request a copy. Because this is a live presentation, I apologise in advance for any technical hitches. Touch wood, it's not been too bad so far. Before I hand over to Philippe, I wanted to mention that this presentation has been granted AIA approval as a continuing educational course and will gain a 1-hour learning credit. Here you can see the learning outcomes of this event, and Kuraray is a registered provider with the American Institute of Architects Continuing Education Systems. Credit earned on completion of this programme will be reported to the CES records for AIA members. Certificates of completion for non-AIA members are available on request. So this programme is registered with the AIA CES for continuing professional education, and as such, it does not include content that may be deemed or construed to be an approval or endorsement by the AIA of any material of construction or any method or manner of handling, using, distributing, or dealing in any material or product. So now I would like to introduce Philippe so he can go through his very interesting presentation.
Thank you very much. Well, it's a pleasure to show 2 projects or 3 projects from our office. The main project is, of course, the Audemars Museum, the Musée Atelier in Le Brassil. For Lushinger Meyer, the project was a really important special project, and I think for one reason it's a fantastic outcome. It's as good as promised in the competition stage, but just starting with the competition stage, it was privilege for us to join the Bjarke Ingels Group team already at a very, very early stage, working on the concept of the museum, developing it into the double spiral shape. We started that competition 2013. It was quite a good year for us because we won actually 2 watch museums with some similarities, but also in very different context geographically. If you have a look at the museum as it's shown on the competition rendering, it's a project, a building, which is quite moderate from the outside. So it's just coming as a sculptural building out of the landscape of a small village, small city at a very rural area of Switzerland. On the other side of the houses, there's just one of the long streets where the houses are located at. It's most of the time long villages, long cities along those main roads. And then it just goes a bit in the width. Our project really is on the edge from the village into the countryside. So that double spiral just comes out of the earth with that special shape. It's beautiful from the outside, but we believe it's really kind of the very special part is shown from the interior. The project is promised as an all-glass structure in the facade level and interior partition walls. We have a roof. The roof is just sitting on the glass partition walls and on the facade glazing. So that's what was coming out of a very intensive competition work. We started with very different schemes with concrete boxes, and it was just developed at one point. It was very clear that this is the very right scheme for the use and for the client. I think today we can actually touch three main topics connecting actually the different projects. One is just the equilibrium. We had to find a balance. Of course, structurally, we had to balance the steel roof on the glass elements and to have actually a robust construction. That's one perspective of the balancing the project. And the other one was, of course, the use, the energy. So the design criteria, which suddenly has proven to be as important as just a structural calculation. It was very much about creating a sustainable glass building, which is not so easy, but also doable with good partners, good products. And the other one is just kind of the very high visual criteria from Audemars Piguet. And I will just follow up on this one on further slides. But before that, we come into the second topic. It was about the tectonic. It was really kind of about that glass building with big architects to find the right way of finding the shape, but also finding the way how we would connect the different parts. So how the glass is meeting the steel roof, how it goes into the ground. So that was really a lot about how stuff is put together. And on that occasion, we were again exposed just to the very, very high expectation from the client. As you see really well, watchmakers, they have a viewing distance of a couple of centimeters to their products, to the very high-end product. Audemars Piguet is really one of the last family-owned watch maker company. They are developing mechanical watches with very, very interesting mechanics, but also kind of all visual parts are in a special material, very, very done in a very nice way. So that's actually the viewing distance, and you see just kind of the detailing of a watch. It's a Royal Oak, probably the most famous Audemars Piguet watch. And you see kind of bolts, but you see also the bolts are shown for reasons, not for need. And that was one point of the project, to find, beside the material, really the way how we are fitting the stuff together. And the third part, it's kind of the material. So the project is a lot about brass, kind of raw, natural material. It's a glass, also kind of a material which should be as raw as possible, coming out of the float plant in an annealed state to create a perfect surface. This picture just shows a project from very similar in a way that's glass, but just kind of from the material, a total different approach. It's with made-in architects at the train station in Zurich, where we work with glass. And the glass in that occasion, of course, in a casted way, it has a completely different quality, but it's also a project which was a lot about the expression of the material, the haptic of the material, and how you just see it with the eyes, how you notice it in the real building. So that's how we started into the project. And you see, we have a lot of glass. You see, in the end of the project, I just show you a picture, a real picture in the same perspective, and I could also show you what it changed in the project during that process of developing a glass project, but also meeting kind of high-end sustainable labels. Starting on the competition or working on the competition, of course, it's always, for us as engineers, we are looking for analogies, just looking into other project, how stuff is done. But I think also kind of from the architectural point of view, the watch was an important part of the project. So finding the shape of the project. And if you just unroll the double spiral, you just notice you have actually a perfect museum path in a linear way. In our case, because it was developed with a double spiral, you go into the building. At one point, you're just entering the center part, which is a bit larger from the diameter of the space, and you're just going again out through the spiral in the historic buildings. And actually, that mixture between developing the shape or kind of the architecture out of a watch, just as an inspiration for us as engineers, it was a great chance because the shape was also defining quite moderate spans. You see, it's just kind of winded up the double spiral, and suddenly, although we have a 30 meters diameter, the spans of the partitions were quite moderate. So that was actually a chance, and that was when we actually really moved into it and promised or proposed, let's go for glass and only for glass. Actually, to get glass in a shape as a curved element, but also from the mechanic of the glass in a pressure loaded component, which glass is very good. So it was actually, I think this one was somehow a bit like from the idea, from the principle, how the structure is working. That was a bit a breaking through point, coming out of different kind of proposals, going into the double spiral, having an architectural shape, making a lot of sense to the project, but also giving a lot of opportunities to us, to the structural engineers, to have a dialogue with the architects, with the archangels group, developing the structure of the building in a holistic way of the whole project. You see, as it's kind of a bit in a slope, it was not so easy, geometrical wise. So we have a lot of steps. In the concrete, it's easy, but it's already kind of a beautiful ceiling if you're just in the car park area because you have that spiral visible. But we had also to stack the glass. So the load-bearing glass was actually on one side just a partition wall as laminated glass, and suddenly a bit further up, it's an insulated glass unit. If you have a look on the whole project, we have just the spiral. We have just kind of the founder's hall with a flat facade, also load-bearing, the outer part, which was actually from the build-up quite decisive for the whole project. And then we have just kind of both the historic buildings and just the side buildings in the ground. The project had quite specific conditions from the context. I said it's in a very rural area of Switzerland, which means it's approximately 1 hour out of Geneva or out of Lausanne, in a valley quite high up. It's around 1,000 meters above sea level. But it's not going to the Alps, it's going actually towards France. And that has just kind of some microclimatic conditions. One is just kind of, it's one of the coldest area of Switzerland, although it's not in the Alps, it's just with the funneling effect, it's really kind of the air is just cooling down in that area a lot. So it has a lot of snow, or it can have a lot of snow. And on one side, it's that snow, kind of powder snow, it's very cold, but that's not the issue. It's also kind of in the mid-season, or changing from winter into spring, where the snow gets really kind of wet and heavy, and it snows again on it. So the snow loading was one criteria, but also kind of meeting kind of just kind of the architectural context of that place. So I said, very cold. On the other side, from the client, high demands on sustainability. In Switzerland, we're working with that Minergie criteria, which is actually tightening up the building regs, but also focusing a lot on comfort. So we have to make a sustainable building in glass beautiful as possible, but also kind of comfort-wise on a quite a high level. On the left side, you see just a mock-up, early one, and you just see it's frosted glass, but it's frosted glass because it's really frost on it. So it's really like, that's when we built the mock-up. I showed it later on, more pictures of that. So kind of snow, cold, frost was an issue to the project. Also changing then in summer times to quite higher temperature. So we had just kind of classic facades criteria to work with. One is just kind of really air tightness, water tightness. That was actually the criteria which are important, but also quite easy to meet. I said kind of the snow loading was a big point, but we had to expect 500 kilos per square meters, but due to the snow drifting of the roofs and the shape, in some areas we have just to double the snow load. So they're more or less on that roof, we had to expect in some areas a ton of snow per square meter. So that's a bit of load. And on the right, you see just kind of the demands out of the function of the building. It's very expensive watches. And the burglar resistance, the redundancy, kind of the robustness had to be really, really high end. And that was actually when kind of the interlayer, the centric glass, was kind of kicking in as a product at the first time. So we had actually to provide a glazing which is quite burglar proof. That was actually a topic growing from meeting to meeting in the classes. So every second week or every month, the criteria on the burglar resistant actually grew a bit because it's a glass building, so most likely not that robust. But at the end of the day, with kind of testing, we could also show the client and the consultant, just from a stomach feeling, what it means to break glass, which is laminated. The decisive criteria from the shape is one, just kind of the roof drainage. So we had to find a way how we could actually drain the center part. In the competition, we had actually two steel elements in the center part actually helping where the span was just in length exploding compared to the other one, but mainly just to take the roof water down in kind of a safe way. And I think that was actually one quality of the project. It was kind of not going, once you're going SDDD into a process where you just kind of lose precision, where you just ease condition or kind of you had to make it cheaper. No, that was not the case in that project. Of course, we had to look after the money, but it was also a very strong commitment from the client and also kind of a very strong demand from the architects to find good solutions. And one was, of course, if we go for a glass building, it has to be totally in glass. So the roof drainage wasn't an option anymore. That meant the shape had to be adjusted. So it was just kind of the center part is just drained out just over the glass. It's just working. And for us as structural engineer, one of the main challenges was kind of the robustness and the robustness of the center part. That 5 meters of the side span, that's actually quite easy. It's complicated because we're stacking glasses. So from insulated glass unit into a laminated glass unit, getting the forces through, but also having a nice thermal insulation line. In the center part, suddenly the span was not 5 meters, it's a bit more than double, which means kind of a lot of concentrated forces on some glass panels. Beside that, we had just kind of the deal what we have all glass project to balance the G value with the U value, with the shading, and with the transparency and light transmission. And it was quite a good coincidence. In the same year, we won another watch museum, which was very fast in the beginning, but now that project is not built yet. That will be finished, I think, 25 or 27. So a very slow project, but in the beginning it was fast. So we could actually start already to investigate some glass solution. But just to give you a bit of context to the other watch museum, this watch museum sits actually really in the center of the Alps. It's approximately 1 kilometer off the Jungfraujoch. You can go up by train. The museum is around 3,700 meters above sea level, and that's really kind of an alpine condition. So first, it sits on a rock just beside a glacier, so actually the access goes through an ice tunnel. And that watch museum was also very glassy, but kind of transportation-wise, a bit of a challenge. Everything has to go through the tunnel. It has to be in transportation mode already quite quite robust. So on that project, we are working with a high transparency. We have also to deal with kind of the shading, just coming to that. But the main building of that watch museum on the Jungfrau Ostgrat, it's actually the building itself is a watch. So we have 3 cylinders. The slowest one turns around once in a month, the second one once in a day, and the fastest one once in an hour. So you're coming out of the elevator shaft and you're in the watch itself, and you experience, of course, kind of all the mechanics, but of course also just a very fantastic view into the glacier world. It has a bit the issue that already in minus temperature, and it's almost every day -5 degrees or less, you have an overheating challenge on that because the sun is so intensive in that time. So the building was composed with a facade, and as I said, we had to go through a tunnel. It had to be robust. Helicopters were not really good for installation. So first you have to build a building to build the building, and everything has to go in. So we worked with the transparency and just saying we're building up a truss. The truss is the channel, actually the energy channel. So the sun heats the facade, and actually the heat, the energy just goes straight out in that spatial facade structure. And the energy which is too much is already out of the building again. To achieve kind of the transparency aimed, we replaced the truss. All digital diagonals have been taken out, and we started to use glass as a bracing element, which brought us actually to the topic of the Audemars Piguet watch, to use actually glass as a structural element in compression. On that project, I said we have just kind of an interior insulated layer, and then we have the glass elements in quite a robust way, kind of by the pressure caps from the inside glazed, but the load from the diagonals goes through the glass. So that was actually the idea which we developed on a side road and which we're just taking into the Audemars Piguet project. And on this project, of course, the glasses are much larger, much more heavy, but from a pure structural point of view, the glass is serving in the same way. On the Audemars Piguet, we have kind of the steel roof sitting on the glass, and the steel roof is quite an important part of the project because it has to make sure that it's quite stiff in plane. So the roof, you see, it's a lot of kind of diagonals. You have just to make sure that the roof is stiff and transferring the horizontal loading quite equally in the glass elements. You have just to manage in seismic loading, you have an action, and actually that action has to go to glass panels, and it has to distribute over several panels that you can actually take the horizontal loading. It's really clear those glasses are not just a pendulum column taking the heavy snow load on top of it. So it's kind of, that's actually the easy part. The difficult part was actually to provide actually the lateral stability of the building with glass units. Just the organization of the glass structure is kind of the green panels, it's triple glazed glass units, so providing actually quite a good U value of the thermal envelope. It's really the green one, and just say at one point the green one go on the red one, and the red one, it's actually just a partition wall, providing kind of the volumes inside the building, but also picking up in the center part the concentrated loads. So we were just actually able to adjust the glass build-ups in those places. If you see the glass as just graphically as a simple component, we have just kind of the support at the top where we're just getting in the compression loads, but we also see kind of the horizontal arrow just showing the lateral forces, which brought us in some load conditions to the situation that we have a lot of pressure on one side because the glass wants to tilt in that direction, and a bit of tension on the right side. And that tension was so little for the glass, it was not a challenge, but of course for the connection at the bottom, at the top. And on the right side, the compression force in the glass was a bit a challenge due to the stability, but mainly to actually get the concentrated forces from a steel component into the glass. The solution was to provide a shoe where the glass sits in. Where we get compression forces in, we used epoxy mortar to get really from this metal component through epoxy mortar, the compression forces into the glass. That's where we have just the compression pads, or so-called pads. And for the tension and sidewise stability, we used silicon to have actually the glass embedded into the steel shoe in quite a nice way. So those forces are just distributed over the silicon. So a very gentle way of introducing the forces into the glass. And as structural engineers, most of the time we like kind of the clear load path. And in the beginning, for a while, we've tempted a bit to actually say, okay, in the shoe we have point fixing, so we actually really know where the forces are going into it. But for glass design, that's not really kind of the best way for the glass, for the material properties. In the glass, it's always where you have kind of the micro flaws in the glass. That's the point where it starts to fracture. And around the point fixing, you have the stress concentration. So just thinking as a structural engineer, it's a nice concept, but coming from the material, it's not really the solution. We could introduce forces or high forces into glass. That's why we went into a solution where the glass has a bit of shape, so it fits in the steel shoe and provides a nice silicon joints in the visual area, but the glass is actually just by form locking in a steel shoe. And the steel shoe is injected with the Hilti epoxy mortar, where you have the concentrated forces, and you see just kind of the hinge from the kind of the structural system. The glass can just tilt inside, out of plane without any restraints, but sidewise, it's actually the point where we just get the force into the steel and from the steel into the glass. You see on the side of the shoe kind of the silicon points in the holes, and that actually holds space in a way that the two component silicon could actually get hard, build up kind of the strength, but also to inject the silicon into the shoe. You need quite a bit of pressure to get actually the silicon through such a small hole, press it in until it comes out at the top, or you see it from the next hole, and then you press in this one. So actually it's really kind of filled up with a two component silicon, and it works because you have also kind of those holes for the hardening process. So that was kind of more from the pure technical tectonic, how we get the glass in shape that it can take forces. And the solution was really kind of to give a form, being embedded in silicon with pressure pads. The other kind of important topic was kind of the surface quality. And that's really where you get back into the watchmaker's viewing distance. It was really not an option for the client, for Audemars Piguet, to have actually a glass thermally strengthened, where you just see kind of that surface distortion. That was really kind of total no-go. Structurally, of course, we would have liked it to have a stronger glass, get the forces in a better way, to have a better thermal resistance, but this was, I think, on the second meeting, totally clear. The client would never accept a glass which not provides a very, very high visual quality. And that was, for us, I think, the largest challenge, actually, the points which you just woke up at night and just said, oh, a nude glass and that use, how we're going to make it work. But it was really worth to go that route, also with the assistance of the industry, from other consultants, to actually get the glass into a shape with an edge finish, which allows us to use kind of a nude glass, as curved glass. Early in the project, prior going into tender, we had the chance to build up a mock-up. And that mock-up was for several reasons. One was for the client to see the glass quality, to prove him already on the mock-up that actually the glass on the building is in a perfect shape, and not what you see just kind of in trade shows, kind of fancy curved shapes, and then you look into the glass in a flat angle and it's all kind of distorted. That was really kind of the fear of us, but also from the client, that we're doing a great project, but in a small viewing distance, it's not kind of meeting the quality. On the other side, the early mock-up was in a way just to prove that the base principle of the load-bearing glass works. So all columns after the mock-up was finished was just taken out in the front, so you could really show, in principle, it works. For us as engineer, it was once installation sequence to get a bit the feeling of it, but also kind of to get confirmation of the technical principle of joining the components together. You just see kind of the large glass units lifted in by the crane. So it's kind of 2 tons which are just juggled around, which you have just to get into the place and lock it up and load it in a controlled way. A further question on this one was actually the coating of the glass. On the right side, we see kind of in a flat angle, very good quality of the glass. But we had also to meet kind of the sustainability criteria. The partition walls, you just see that's an annealed glass, laminated 3 x 12 millimeter annealed glass, no coating, super transparent, super finish. And then behind that, you just see what was our kind of proposal to the energy guys. Let's take a glass with 27% G value. And the rest of it, we maybe can compensate with PV cells to find actually a way to have quite a bright building. At the top, the small panels, that was actually the proposal from the energy guys with just kind of 23% G value, quite a dark glass. And that was the point which we were just a bit nervous about, just to build a project. And of course, in the end of the day, we had to follow kind of the proposal of the energy engineer that we had to control the sun intake, the solar load. So the building is going to be built with that 23% G value, quite dark if you see it, and if your eye is just building up a reference to the clear glass or to the sky, you think it's a bit of sunglass. But I will show you the picture as finished. After the mock-up, the tender was taking place quite quickly. Kuraray was joining as a specialist facade contractor, having a lot of experience in structural glass. They just finished kind of the Steve Jobs Theater as a not insulated building, but of course a lot of competence in structural glass, but also kind of all the building physics as kind of a facade consultant. They had a lot of experience. So with Kuraray, we start the process in the execution stage. One was, again, quite early to have reference samples. This one is just kind of the first samples at the works of Kuraray, showing again kind of the quality that now as it's tendered out, it's contracted, kind of that chain is working well. And on the right side, you just see kind of the structural glass build-up of the load-bearing glass, with kind of the annealed glass, the centric glass interlayer, and then just kind of the insulation build-up, or the build-up of the insulated glass units in front of that, forming one holistic component. And that was quite an interesting process because we could actually bring some ideas into sharpening the process or kind of the design, using all the kind of silicon to spatule the non-visible areas just to avoid that kind of light is just coming in from a side you don't want. So if you look into the shoe, it's just kind of perfect black silicon and not kind of from the side, a bit of light going into the shoe. The structural testing of that project was, for one reason, kind of going to the last point of the project, actually to prove the robustness, the structural robustness, how we're getting actually the concentrated loads into the glass. That are just kind of small samples which we did already in SD, just in Lucerne, at Lucerne University in the lab. We were just already kind of testing how we're getting the load, the concentrated load into the glass, also developing the feeling for that project, what's the solution. It's always interesting to see those glass mock-ups, test specimen. Also, you can read a bit the stresses in the glass, how the stresses are in the glass. It's always breaking particular. But it's also impressive how the glass just explodes if it breaks at a high stress concentration. That was just kind of the small samples getting into the project. But being on the way of execution, we had still kind of the hot topic, the burglar resistance. That was kind of solved, but everyone was like a bit like it's a glass building, very expensive watches, millions of Swiss francs of watches just displayed. That was one side route, which was still kind of, everyone wanted actually to finally confirmation how good the glass is. For us, we have been interested, of course, to know what's happening if one glass fails totally. If it's broken from both sides due to damage by burglars or whatever, we wanted to prove the post-failure resistance. We wanted also to prove on the exact detail how the load transfer of the final design works, but also kind of showing the post-failure resistance and just showing that the glass can take actually more load in an accidental load case if one glass just is taken out and it has to be transferred to the other glasses to the side. So it's a glass specimen here. It's one of the central glass units in the center part of the spiral, where we have 5 times 12 millimeter annealed glass loaded up, and kind of the test rig with hydraulic jacks, kind of taking a lot of measurements. And in the end, it was quite successful. It was very successful in the test rig. We had also kind of to break the glass to get it into a state where we actually, all exposed glass was broken. And that was also a bit the breakthrough regarding kind of the consideration of the burglar resistance. It was really impressive how much mechanical force you had to get in, just into breaking one glasses. And then you still had more layers, unbroken glass. And we did the same on the other side. And the glass component 5 times laminated glass, annealed glass with sentry glass interlayer, 2 panes broken, was still able just to take 80 tons or just the locomotive on the glass for quite a while. We had just kind of a weak loading on the post-failure situation. So that was actually for us kind of the last important step before getting or bringing the glass to site. And for us, it was really kind of striking how nice the glass was produced, how nice it was installed, how good the design was. But I think one of the main points is really kind of the transparency you're going to experience in that building. Shown on the situation where we had the mock-up with kind of the different glass samples, it was always kind of the eye was referring to what you see, what the glass is, and then on the left side, it's just kind of no glass or nude glass, and that just made the glass quite dark. In the Audemars Piguet Musée Atelier, you're just in a glass world. You're looking through a lot of glass, so you have just to imagine you're in the center part. You have a package with 5 times annealed glass, 12 millimeters. Then you have another partition wall of 3 times 12 millimeters, and then you're getting to the facade, and again 3 times 12 millimeter glass plus the IGO on the outside. So you're in the building and you're looking through a lot of glass. It's all kind of low iron glass, of course. The facade has just kind of coating to provide the low G value, but in the glass world, the eye is not building up a reference and it appears totally transparent for the visitors. So I think it's really kind of, first time I was in the project was still a bit the building side. It was just kind of very, very nice to see how nice the transparency is, but also kind of the precision of the execution. And possible was really because it was a multidisciplinary effort, just with Bjarke Ingels group as kind of lead architects, but also because of the other consultants, having that dialogue with the energy consultant, finding a way to actually provide enough shading, but also providing enough transparency that it's just a striking building. But also, you need partners from the industry. One is just kind of the glass processes, but then just the supplier from the interlayer, the sentry glass, but also kind of having Kuraray as a special facade contractor on board. So that was just kind of, it was just kind of cool to see that building finished. And in the beginning, I showed you just kind of that very clear rendering where just everything was just dissolving into nothing. And then you just have a bit kind of the reality. But I think the outcome of the reality is on that project really, really nice. On one side, it's the glass quality, the surface quality, so almost none kind of distortion. The other one is the joints between the glass where it's just kind of an open joint or a bit of silicon if it's just having some sound criteria. That's just kind of those joints. On the right side, you'd see the joints, which are just kind of a fact. If you just use insulated glass, you need the spacer, the sealant of the space is a joint between, and that's if you just imagine, I'll show you on the next project what it means in dimension, but on the project, you have just kind of those small black lines. And if you have the right viewing distance, it's just also kind of disappearing into the construction. So just, I think it convinces in a very natural way. So, and if you're from the outside, that's actually the same view from the rendering. You see kind of the double spiral. What you see, it's really a building which is very beautiful from the outside. In summer, it's green, but then you have just the realities. One is, of course, the balustrade. I think that's just what it has to be. On the other side, the topic of having transparency versus the G value versus kind of an exterior shading device. I think that was quite a good marriage in the end. If you're on the inside, the brass, it's really kind of brass in natural state, very beautiful, building up a nice patina, but it's always above eye level. So if you're in the building, you just look through the glass, and if you look up, you have a nice pattern provided by that bespoke shape of that shading device. So I think it was really kind of, that's, I think, very beautiful. And there was also kind of, from Bjarke group, just kind of focusing also on the blinds until it was really kind of meeting the project. And for us, a big pleasure to be kind of part of that team as facade and structural engineers. So as I said, it's a project partner required. One is just, of course, the client and the architects, but also kind of Reif as a facade contractor, but also kind of the industry actually supplying the product that you're able to build such nice projects. But also kind of small players like thermal assessment from glass for concept, just helping us with kind of the thermal robustness on the glass just on the edge to get actually the annealed glass into the project without glass breakage to thermal actions. The last project, which we're just kind of touching a bit, it's a project which we are working on right now. It's a project which we started last year. And it's in Copenhagen. It's just next to the Royal Opera in that kind of new island sitting on top of a car park. And it's again a glass pavilion in an organic shape, quite tall glasses, very transparent. And we were just able to join that project in a bit later stage. It has a lot of similarities, but of course, it's also kind of different context. And between the project, also if it's kind of the project is maybe visually or architecturally not so similar, we're always looking a bit between the project or seeing them a bit as relatives from engineering point of view, actually grabbing or taking the good stuff from other projects, also from competitors. If we're seeing nice stuff, we're also trying to challenge that on our project. This one started in the logic of the Audemars Piguet Museum. So again, yes, it's cool, it's structural glass, and we have even more experience than before the Audemars Piguet. So we're really joining the project with a focus. We have that floating roof, again, a green roof. We had some kind of shafts because they needed elevators. So it was already starting a bit. It's not only glass, it has also some service inside, actually enforcing some opaque components. And if you're looking into it, it's kind of the parking area on 2 levels below ground. And then we have just kind of, that's a rendering from an early stage, kind of the roof in a very slim state, and the glass taking up some nodes. Having a bit a closer look on the project, actually starting already really in the logic. Yes, it has to be structured glass to achieve the transparency. We had a second look on it, and that was mainly coming out from the office from Lausanne. They were just acting as a structural engineers on the project. And we are from the Zurich office into the facade design. And although we have just been separated to that COVID stuff, it was quite a good dialogue developing stuff. And they brought a really cool idea from a structural point of view, which was actually having a real impact on the facade. The Audemars Piguet Museum, as a reference, we have just kind of only glass. Everything is glass. We have the steps, the roof structure is not kind of spanning over 2 elements. So it has a lot of similarities, but we have not a continuous roof structure just in the line perpendicular to the glass, and it's only glass. On the pavilion in Copenhagen, we have a larger kind of diameter, it's 45 meters, but we have some opaque elements and the glass line and then the elevator shafts. So there was just kind of a different context to play with. And that was actually, I said, we were again in the glass world, and the idea coming from the structural point of sight, we could actually pre-stress the roof. So we have very few kind of areas where we have just kind of solid parts, which are just kind of ductile, easy to handle. And then we have just huge cantilevers and the glass. And of course, that's a difficult match, the cantilever going up and down, or particularly going down. And on the right side, just saying, okay, on this project, the glass is only a pendulum column. It's only taking compression forces. The horizontal forces we can take through the shaft. And the idea of having a pre-stressed roof was actually in the joint of the glass, we are having a kind of column. And the column is actually a pre-tensioned lamella pulling down the roof. So that needed a bit of effort just to explain also to the project partner, because from a first point of view, you have a cantilever and you pull it down. That was actually the proposal, freeing the glass from many kind of restraints, making the glass more to infill, but getting all the complexity into the joint. You see, we have just kind of the course where you have the elevator in, you have a column, but then you see it's a lot of span and a lot of area where you have only glass. So it's a much more hybrid element or hybrid structure. You have a bit of traditional elements, you have a facade line, huge cantilevers, and we changed from kind of load-bearing glass, picking up actually the cantilever, to tension columns, or kind of pre-tensioning the roof. And we built a small mock-up in the office just to explain the effects, how we want to make it work. And basically on that mock-up, you see kind of two cantilevers. One is just going out in a straight way, and the other one is just going to the sky quite a bit. And then we are taking actually a rope, pull it down. So it goes down. And the cantilever, without kind of the pre-tension down, if you put weight on it, it just sucks down, just a natural deflection. If you put the same weight on the cantilever, which is pulled down, nothing is happening as long as the weight is less than the tension force down. And that's actually the trick or the innovation of that project, that we're actually pulling the roof more down than we have snow loads and build-up loads. So just to explain, I'll just illustrate it in a bit the easier way. That's just kind of the mock-up. If the weight is hanging on the pre-tension cantilever, nothing is happening. If you go to the other one, your cantilever goes down. That solution would require a glass column below. The other option, if you have just a tension element, the pre-tensioning, you could actually start to hide that just in the silicon joint between the glasses. We need a lot of force, around 75 kilonewtons. Design forces, there's just kind of a variety of different materials. Of course, carbon fiber is super good, but not so easy to get the forces in. At the end of the day, we are going with a stainless steel, with a lamella 20 millimeter by 5 millimeter, which would actually start to play with the joint with. I'm just saying, at the Audemars Piguet, which is very transparent, we have two joint build-up. One is just the one from the insulated glass unit, which is basically 55 millimeter by almost 100 millimeter. That's actually the opaque element into the transparent glass unit. Just matter of fact, it has to be like that. Or kind of the inner wall where you have just kind of a structured glass build-up with kind of the silicon infill 15 by 53 millimeters just in diagonal. We have just kind of that width of 52 millimeters. On the greenhouse, on the start point where we just joined the project, we had a structured glass element 3 times 8 millimeter and the joint build-up, all taking up tolerances. And our proposal was aiming for a solution where we have actually the tension lamella in that glass joint. So the joint gets a bit wider, the glass build-up gets a lot more slim, so only 2 times 8, which means actually the diagonal of the silicon joint is pretty much the same or a bit less. We have there 25 millimeter in diagonal, there we have 31, or we just start to embed the tension lamella into silicon, so it's fully hidden. So you could actually have also around carbon fiber in that joint hidden. But starting to do that, we are starting again to talk about tectonic principles in the facade. So first, then the fun starts a bit. It's a bit like the fun of having a structural system. It works, but also kind of the detailing. And the detailing starts a bit afterwards. So you have to have a good bracket for the glass. But the main topic in that project is actually how we play around with the tension lamella. So it could be a tension lamella being just quite slim, looking out on both sides. It could also be a tension lamella going into the building, a bit like a knife. On the outside, it's fully flush. You could embed it. You could also turn it around, have it be the offset. So you have actually the glass layer and then just the so-called piano wire pulling down the roof. So that's on the second project, how we are working. Coming from the Audemars Piguet was kind of the load-bearing glass. On that project, we could actually free the glass a bit from the load-bearing function by just a very small kind of tension element, providing actually a better transparency because it's only a third of the glass, only one interlayer between and not two. So it's one side a bit cost saving, but also I think in the end of the day, the project at the pavilion was kind of the context of having some small kind of big build-ups, shafts with the elevators, a couple of columns. I think we're just making the building much better by those elements. But it's, to be said, it's a project which is now going into execution, but we have just kind of a different technical context from the structural system, providing both a very transparent facade. This one, tensioning down the roof, and on the other side, we have the Audemars Piguet Museum, where it's kind of fully load-bearing, and we have it already built with nice joints, slim. So that was just kind of the journey I wanted to take you with structural glass and the interlayers, and also showing the benefits of those complementary glass interlayers, structural silicon, and these. Thank you very much.
Wow, congratulations. Well done, Philip. That was a fantastic presentation. Thank you. And there has been a few questions that have come in. Can I put some questions to you? Hopefully you'll be able to answer them for me. There was a question that came through that mentioned that the design process originally for the spiral, it was there was a few other parties involved in that design process, and you put credits to Bjarke Ingels as also as one of those. Who actually came up with the idea of the spiral? Was it yourself? So
no, that's spiral. I think it's very nice to be in competition with Bjarke Ingels group because it's really in the beginning, it's totally open-minded, but it's in a very structured way. So it's testing a lot of ideas, and you're just part of that kind of race through that competition as engineer consultants. And you can just give a benefit out of your disciplines, but also kind of out a bit of your stomach feeling. It's a kind of that design process of developing a building. The idea of the double spiral, that was clearly an architectural decision, just coming out of the watches, the mechanics, having actually that double spiral. But we really like to be part of early stages because that's when you could actually bring the benefits out of our engineering into the project in a holistic way. So it's really like early stages, you can discuss, you can test, you can just, okay, that was not the greatest idea, let's try this. And that process actually makes good proposal. And for me, it's often so you need, maybe the first idea is the best one, but you need a couple of other ones just to find out that the first one was the best, or you develop through iteration of proposals again and again with a nice solution. And of course, the spiral was really kind of, for us, as we saw, it was quite clear, well, that's the project, and there we would really like to go full speed.
Yeah.
With glass and as a structural element.
And I bet it was probably your worst nightmare for the client to decide that they wanted to use annealed glass, because more often than not, when you're looking at structural performance, you're looking at toughened glass with laminated interlayers. And so during that process, You mentioned you mentioned the brand, which I thank you for. But with regards to Stiff or the Iona Plus, were there any other alternatives that you considered that would give you the performance that you were looking for under those circumstances?
Well, of course, we had to be also in a financial kind of context, and of course, that project was kind of really the client helped a lot on that project that we could actually build. It was not that process where you just have a fantastic competition proposal and then you have to go back because it's too expensive or just kind of too advanced. No, they really kind of pushed for it and just said, no, it has to be fully glass and it has to be in a good quality. And for a while, we looked into chemical strengthened glass just to have actually a better performance, but that was actually size-wise a bit critical because there was only one supplier providing that size. It was very expensive. So I think the project is also good because we managed to build it, get it with a good edge finish into a way that the annealed glass works. And it's kind of a base quality of the glass, but in the pure stage. So it's nice, but also kind of being in the context of the financial restriction or the target, you have to say.
Yeah, well, thank you. And just one last question, and it's, thank you very much for the bonus slides, by the way, with regards to the Opera Park and Pavilion. Again, another beautiful project, and it just goes to show very, very similar actually to the Steve Jobs Theatre, where you have the roof structure supported by glass. And so with that particular project, you mentioned using tension lamella between the glass panels. Now you're very heavily reliant on the structural silicone to maintain that effectiveness. How did you compensate for thermal effects of expansion and contraction to ensure that tension is still maintained?
Well, you have just imagined the tension lamella picks up the roof which is far too high installed. So it's maybe 30 centimeters too high. And then you just pull it down a hydraulic jack. And then the tension lamella goes from the roof structure into the foundation. And you pull it too geometrically to the right level. And the glass is really kind of the infill. And if the roof tolerances, if it goes a bit down unexpected or there's movement, you could have slot holes because the glass is not loaded anymore. The silicon joint or the joint is really kind of the decision for weatherproofing and to hide the tension lamellas. For instance, if it's a carbon one, we would really like to hide it into the glass. Or if you just use it as a tectonical element, you can also play with the lamellas, hide it, or just use it a bit as a blade sticking out or as a kind of a cap or kind of a lamella sitting in front of it. But you've always to imagine it's kind of a huge building and your tension lamellas is 5 by 20 millimeter. So it's kind of, if you see it in the context, it's really like a piano wire, a tension one.
That's great. Okay, well, thank you very much for your time. Just before I say goodbye, I would like to promote a presentation for something that we have planned for next month. I don't know if I can just share my screen. Bear with me. This is a presentation that we've planned. It's actually a web seminar. It's a forum, so it's actually a panel discussion, and it's something that we've not done before. So we're very delighted to be able to hold this. We've got 7 panelists from Europe and the US involved. Our very own Steve Benison and Ingo Stelzer, but also they'll be joined by Professor Gianna Royer, Professor Marcus Fieldman, Richard Green, Eric Dupont, John Colvin, and it will also include 4 presentations and a panel discussion on the effective thickness method of design laminated glass, comparisons between different methods of calculations with practical examples, stability and local stress calculation in laminated glass, and which effective thickness to use and when not to use it, and code activity that's going on in both Europe and the USA. So I'm confident it will be a great debate with lots of discussion, and we really would welcome you all to attend on April the 28th. Information will be available on our website from next week. So please do tag along and keep an eye out on social media. And that's it for today. So thank you very much for your attendance, and hopefully we'll get to see you again very soon. Thank you for your time. Bye-bye.